In the last lesson in this unit, we're going to talk about the fundamental theorem of algebra. There's two parts to this theorem. The first part says that an nth degree equation has exactly n roots. And we've talked about this a lot. Whatever the degree is, that's how many roots you should expect to see. So an nth degree has exactly n roots. Now, typically we know that an nth degree equation can have at most n real roots, but in the complex numbers, if we also include the complex numbers, that means that we have exactly n roots. So this just means that we could have some real numbers and complex numbers to get that total number of roots, which we've seen this entire time. So basically you just look at the exponent, the highest exponent, and that's how many roots you're going to have. So if you look at this example, it says state the number of roots or solutions for each polynomial equation. So you look at the degree. The degree of this first one is a degree 1 because the highest exponent is 1. So that means there's going to be one solution to this equation. If you set it equal to 0 and solve, you'll find that you'll get one solution, which would be x equals 2 in this case. If you go to number 2, the number of solutions, well, you look at the highest exponent, which is the degree of the polynomial, and that means you would get 2 solutions. If you had a degree 3, like this one, the highest exponent's a 3, that means you're going to get 3 solutions. And when we say we get this many solutions, it doesn't mean that there are going to be 3 real numbers, but it might mean you get 1 real number and then you get 2 complex numbers. But there's definitely always going to be 3 solutions. For number 4, we're going to have 4 solutions because the highest exponent is a 4. And the last one down here, a degree 5, the highest exponent. Make sure, too, that you're looking for the highest exponent in the entire equation. Sometimes the equation may not be written in standard form. It's supposed to be in standard form where the highest exponent's in the front, but it might not always be. So in these examples, my exponents were always in the front, the highest exponents, but that's not always the case. So just be aware of that. So here I have 5 solutions because we have a degree 5 polynomial. So then the next part of the fundamental theorem of algebra is that whenever we have our complex zeros or complex solutions, they occur in conjugate pairs. So what that means is if we have a plus bi as a root, then its conjugate, a minus bi, must also be a root. So say you have some degree 3 polynomial. If you have some complex number a plus bi as one of the solutions, then a minus bi has to be the other solution, and then the third solution would just have to be a real number. It couldn't be, you can't have 3 complex numbers because you have to have the complex numbers occurring in conjugate pairs. So examples of some conjugate pairs, just to make you familiar with it. If you had like 3 minus I, that's a conjugate pair with 3 plus I. So basically you just keep the form and you just switch the signs. So everything else stays the same. If you had like 2I as a conjugate or as an imaginary number, this is really like saying 0 plus 2I. So that means its conjugate is actually negative 2I, because that would be like saying 0 minus 2I. Now you don't really need the zeros, but you get the idea that you have to have a plus 2I and a negative 2I. And then another example here would be like negative 4 plus 6I. If I want to write the conjugate of that, I keep the negative 4 and I just change the middle sign. So just keep in mind, whenever it's conjugates, it's just the middle number that's changing. So the negatives in front are going to stay negatives. It's just the middle. So let's look at how this theorem kind of applies. We're going to look at 2 ways that we can use this theorem. This first set of examples is really just showing you that whenever we do have a conjugate, or whenever we do have a complex number in one of the solutions, then its conjugate is also a solution. So let's look at this first example. The first example says to list all factors and find all zeros. Remember, zeros just means the solutions when the equation equals 0. So that means I'm going to set this equation equal to 0. And I'm going to go ahead and I'm going to solve it. So I'm going to look, I'm always going to try to see if it factors first, because then I can use a factoring technique. Otherwise, we have to do the rational root theorem from the last lesson, where you look at P and Q and you look at the possible zeros, and then you just start testing zeros. And then from there, use synthetic division to rewrite it as a product of factors. But if you can factor it, that's definitely the quicker route to go. So since I have 4 terms, the only type of factoring we can do is the factor by grouping with factoring out a GCF first. So if you look at the first 2 terms, I have a GCF. I could take out an x squared. And then the second 2 terms, I have a GCF. So since I have a GCF in each piece, that's my indication that I'm going to be able to do factor by grouping. So for the first one, I'm going to factor out an x squared, and I'm going to be left with an x minus 1. And then I'm going to factor out a positive 49, and I'll be left with x minus 1. And then from there, I'm going to have x minus 1, x squared plus 49 equals 0. Now, the question asks us to find all the factors and all the zeros. I'm going to get the zeros first, and then I'll worry about the factors. So now that I have 2 things being multiplied equal to 0, you can really set each piece equal to 0. And typically what we do first, though, is we make sure that we reduced all of these as far as we can go. And I look at this x squared term, x squared plus 49, and I cannot reduce this because it's not a difference of perfect squares. It's a sum of perfect squares, which doesn't have a special factoring technique. So we have to just leave that. So what I can do, though, is I can set each piece equal to 0 since it's a product. And I can figure out my solutions. So x minus 1 equals 0 is going to give me x equals 1. And then over here, I'm going to have x equals negative 49. And then I can take the square root of both sides. And just remember, when you take the square root of both sides, you got to have your plus or minus. So I have x equals plus or minus. And if you remember, whenever we're taking the square root of a negative, you get your i's, and square root of 49 is 7, so it's going to be plus or minus 7i. And if you look, these are conjugate. This is like saying x equals positive 7 and x equals negative 7i. These are conjugate pairs. So that's verifying to you that this theorem actually does work, this fundamental theorem of algebra, that if you have a degree 3 polynomial, you should be getting out 3 solutions, which I did, and any complex solutions, which I have, plus 7i and negative 7i, occur in conjugate pairs. And then the real solution is just going to be, just the real solution. There's no pair to it. So the question, though, if you go back to the beginning, it asks for the factors and it asks for the zeros. So the zeros we already found. That's when you solve and you get the numbers. So the zeros are going to be 1, 7i, and negative 7i. Those are your solutions. Your factors are always going back a step, or it's always opposite signs. So the factors, I have x minus 1, because I'm doing opposite sign. Instead of positive 1, it's negative. And then it's going to be x minus 7i, and then x plus 7i. So those are my factors. And you can always go back into your equation, and if you look back at my equation, I have the x minus 1 factor, but I don't have these x minus 7i and x plus 7i. Instead, I have an x squared plus 49. And when it asks for the factor, it's asking for linear terms. So it's not asking for x squared plus or minus some number. It's asking for x plus or minus those numbers. So just be careful when you're trying to find the factors. Sometimes you actually find the factors after you found the zeros, then you go back and do the factors. Even though in this stage, I'm expressing this as a product of factors, or a product with one factor. So let's look at one more example just to show you this fundamental theorem again, and then we'll look at our last application problem with the fundamental theorem. So the next example here, we're going to go ahead, we're going to do the same thing. We want to find the factors, so this is just a continuation. We want to find the factors, and we want to find the zeros to this equation. So it has 4 terms, so check to see if you can factor by grouping. And basically what that means is if I split it, can I take a GCF out of the first 2 terms, and can I take a GCF out of the last 2 terms? And since I'm going to be solving this for zeros, I need to set it equal to 0. And I actually can take a GCF out of both terms, so I'm going to go ahead and split it. So I can take an x squared out of the first, and I can take a 16 out of the second. And then you're going to be able to take out the x plus 3, and you're going to be left with x squared plus 16 equals 0. And again, this is in factored form, but these factors, we want to express them as linear terms. So what I'm going to do is, since it's two pieces being multiplied to equal to 0, I'm going to split it, and I'm going to set each piece equal to 0. And notice that I can't break down that x squared plus 16 because it's an x squared plus. So it's not a difference of perfect squares. You can't break it down. So I get x equals negative 3 over here. This one I get x squared equals negative 16. You're going to take the square root. We know right away we're going to get imaginary numbers because we're taking the square root of a negative. Square root of 16 is 4. And since we had the negative underneath, we have an I in there. So again, you have 2 solutions. You have your 4i and x equals negative 4i. And keep in mind, these are conjugate pairs. So again, we had a degree 3 polynomial, and we ended up with 3 solutions. And our 3 solutions, one of them is a real number, the other 2 are complex numbers, but they occur in conjugate pairs. So what this means is my zeros are negative 3, 4i, and negative 4i. And the whole reason why we're going through this is because if you were given these zeros, you can come up with the equation, because we know that if we have a polynomial with these 3 zeros, it's the same thing as multiplying it by taking your 3 zeros and multiplying them together as factors, and that'll get you your equation. So if I have these 3 zeros, they came from this stage here where I had them expressed as factors being multiplied together, which really would get me back to my original equation. So basically all along we've been doing it where we've been given the equation, we're trying to find the zeros. In the next set of problems, you're going to be seeing the zeros. You'll be starting down here, and you're going to have to express them as a product of factors, because that's where the zeros come from, is splitting up your product of factors. And you'll write them as a product of factors, and then you'll just have to multiply it out to get back to the original. So we're going to be given the endpoint here, and we're going to be trying to come up with this piece. So it's really important for you to understand the relationship between the zeros and the factors, because in order to go from this endpoint to this starting point, you're going to have to be able to take your zeros and rewrite them as factors so that you can multiply them together. So the factors here, if I look over on this side, the factors are always going to be the opposite of the 0. So it's going to be x plus 3, x minus 4i, and x plus 4i. So those are your factors. And you're going to notice that this fundamental theorem of algebra is actually going to be useful too, because there might be times where they don't tell you all of the zeros. They might tell you that negative 3 and 4i are zeros, but because you know that by the fundamental theorem of algebra that whenever you have a 4i as a 0, then negative 4i has to be a 0 as well, because zeros occur in complex conjugate pairs. So that just is like another application of the theorem. So let's go ahead and look at that, where we start with the zeros and we work our way back up to the equation. And then that'll be the last thing for this unit. So for the applications of the fundamental theorem of algebra, what we're going to do is we're going to use these zeros and we're going to work backwards, and we're going to be able to find an equation. And the reason why I'll be able to find an equation is because we know that whatever the degree is equals the number of zeros. So however many zeros we have is what the degree of our equation has to be. And also, if they give us complex zeros, we know that their conjugates are in there. So for example, we're trying to find a 4th degree polynomial, which means that we should have 4 zeros or 4 solutions, which also means 4 factors. And if you look at this example, we have, this negative here, I'm just going to put it down with the 1. That we have this polynomial that has -1, -1, and 3i as zeros. So the zeros to this polynomial are -1, -1, and 3i. But since we have one imaginary solution, that means its conjugate is in here. So if 3i is a 0, then that means -3i is also a 0. For the -1 and -1, those are just going to be the zeros. -1 and -1 are going to be the zeros. Those don't have any special pattern. It's just when it's a complex number, the conjugates have to be in there. So here are the zeros to my polynomial if it's a 4th degree. And then I want to be able to write the equation of this in standard form. So that means I need to know the factors, because if you want to write the equation, all you do is take the zeros and you express them as factors, a product of factors, and that'll get you the equation. So if I take each of these zeros, I just have to rewrite it with the opposite sign. So instead of -1, it's going to be x plus 1. And I'm going to have x plus 1 again. I'm going to have x minus 3i. And I'm going to have x plus 3i. And then for the equation part, all you do is you take the factors and you multiply them together, and we set it equal to 0 because we're trying to write the equation where these are the zeros. So x minus 3i, x plus 3i equals 0. Now, if it didn't say to write this in standard form, this would be my equation. I'm done. But because it tells you that you have to write this in standard form, that means you need to multiply this stuff out. So when you multiply it out, you're going to do it in parts. So I'm going to start off with drawing a box for x plus 1, x plus 1. And then I'm going to do a box for x minus 3i, x plus 3i. So I have x squared. I have 1x, multiply these, we get 1. Combine your like terms, we get x squared plus 2x plus 1. So I can rewrite that, x squared plus 2x plus 1. And then I'm going to do this next section here. So x times x is x squared. I'm going to have 3ix, negative 3ix, negative 9i squared. So these terms cancel because remember we had conjugates. Conjugate the middle terms cancel. So I'm left with x squared minus 9i squared. You have to remember I squared equals -1. So I can replace I squared with -1. So we get x squared plus 9. So this is x squared plus 9 equals 0. And I need to keep multiplying now. So now I multiply these two, which means since I have 3 terms and 2 terms, it's going to be a 3 by 2 box. So it's going to be 3 by 2. So I'm going to have x squared plus 2x plus 1, x squared plus 9. So we're going to multiply these. So we get x to the 4th. I have 9x squared. I have 2x to the 3rd. 18x, x squared, and 9. So I end up with x to the 4th. I have a like term here and here, so I can add those. I have 2x to the 3rd. I have 18x in there, plus 9. And my expression, or my equation, needs to be written in standard form. So that means highest exponent first, and then in decreasing order. So then it'll be the 2x to the 3rd plus 10x squared plus 18x plus 9. And don't forget about the equals because it said to write an equation. So it needs to be an equation equal to 0. So your polynomial is y equals x to the 4th plus 2x to the 3rd plus 10x squared plus 18x plus 9. So then one last example here, using this whole idea of using the zeros and using the fundamental theorem of algebra to find an equation. So this one wants you to find a polynomial function or polynomial equation with integer coefficients that has the given zeros. So it gives us only 2 zeros, but because you have a complex zero, that means its conjugate for minus I is also a 0. So that means we actually have 3 zeros to this equation, which means we have a degree 3 polynomial. So what I'm going to do is I'm going to first write all of my zeros out. So my zeros are going to be 2, 4 plus I, and 4 minus I. The factors are going to be the opposite signs. So x minus 2. Opposite signs for each of these. So x minus 4 minus I. It's like you're distributing a negative through to each piece, or you're distributing the opposite sign through. So this one is going to be opposite sign for the 4, so x minus 4, opposite sign for the I is going to be plus I. So then when you go to write your equation, it's going to be x minus 2 times x minus 4 minus I times x minus 4 plus I. And what we're going to want to do is set this equal to 0, and we need to simplify it and get this in standard form. So if we multiply these two pieces together first, it'll actually make the math much easier. So let's go ahead and do that. We're going to need a 3 by 3 grid since we have 3 terms in each. So x minus 4 minus I, x minus 4 plus I. So multiply, we get x squared minus 4x, ix, minus 4x plus 16 minus 4I, minus ix plus 4I, and minus I squared. So then what we're going to start doing is looking for some things that are going to cancel and keep any like terms. So we have an x squared. So I'm just going to cross them off as I use them. Then I have x's. So it looks like I have a negative 4x and a negative 4x. So it's going to be a negative 16 or a negative 8x. And then I have an ix and a negative ix. So those are just going to cancel. I have a positive 4i and a minus 4i. So those are going to cancel. I have a plus 16. And then I have a minus I squared. And remember, I squared is equal to negative 1. So I'm going to go ahead and replace that with negative 1. So really, it becomes I squared minus 8x plus 16 plus 1. So x squared minus 8x plus 17. That is just what goes here. So we have x squared minus 8x plus 17 is just from this piece that we have to carry down the x minus 2 equals 0. This is still not in standard form. In order for it to be in standard form, these have to get multiplied. So you're going to be multiplying a 3 by 2. So we have x minus 2 x squared minus 8x plus 17. Multiply these. X to the third minus 8x squared plus 17x minus 2x squared plus 16x and 34, negative 34. So now you're going to combine your like terms. So x to the third, combine these, negative 10x squared, combine these, 33x, and we have minus 34. So up top, when we multiply those, x to the third minus 10x squared plus 33x minus 34 equals 0. So that would be your equation. Remember we said it should be a degree 3 because we had one real solution, one complex, which really implies that there has to be, its conjugate has to be a solution as well. So that means there has to be 3 zeros and not just the 2 that are given to us. So your equation has a highest exponent of 3 and is given in standard form after multiplying all these pieces.